So we are going to start the class number 19, page number 1. Today is October 17th. So if we pick up from the last time, we had this one, right? We run the elastic buckling, Eigen buckling of the problem that we had the pin and pin support condition. So this is what you get in as a buckling shape. So you end up with a half cycle. You end up with this buckling load being P equals to pi square EI over L square. Actually, if you pick up from this point here, so this is for the case where you have pin and pin support. Pin support. So once you get the P value, you know the P over EI. This is equals to pi over L, pi square over L square, P over EI. Okay. And this is your what? The K square value, right? So that makes your K be the pi over L. And then you get this value, you come back to the equation that control your deformed curve, which is the function of y given in terms of x. Come back, we come to this one. So you get B equals to 0, alright? RA is 0 too, so you get A sine KX, and the K is equals to pi over L, and then multiply by X. A could be anything, alright, but 0, not 0. But it could be any value. And we don't really care about the A value. Right? It is just a scale. The part that control the deformed shape is this one. So if you look at this, the sine of pi x over L ratio so your beam from x equals to 0 to x equals to L. So we can draw the deformed shape which is given by this sine function. Sine function start from 0 when a thing inside, okay, here is equal to 0. So you start with 0 at x equals to 0. You're gonna get the maximum sine value when you have sine pi over 2. So pi over 2, you get that value when you're 1, 2, 3, 4, 1, 2, 3, 4. When you are here at x equals to L over 2. Okay. Then we can draw the deformed shape or buckling shape. So it turns out to be a sine curve like this. And then your sine value decrease down all the way until you come to sine pi, which is equals to 0. Okay? So that's why I said that this is the half sine curve. So we don't really know this ahead of time, but we figure it out from the mathematics that the deformed shape is controlled by this trigonometry function sine. Basically, this is what? This is your Eigen vector. And here, the k that you've got from the equation solving is the Eigen value. So today we will continue with another case. Well, we will continue through like many cases that you used to see in the textbook. And you get the k value being 1, being 2, being 0.707, and etc. Alright, being 0.5. A little headache when you enforce the boundary condition here. I remember that every day I got to spend like a few minutes figuring this out. Yeah. So start from x equals to 0, x equals to L. And the system here is subjected to the presence of axial force just like before, the P and P. We have the EI and L. So, if we look at the differential equation, the governing differential equation, we have, let me put the components of this system in. Again, we cannot just assume these forces, lateral forces, and also the moment so you have RA, you have RB. Okay. So if we set up the differential equation, I think we remember that it is A sine kx plus B cosine kx plus RAX over P, and then minus M over P. So what we need to determine are A, B for quantities here. And we've got all of them by enforcing the boundary condition. So let's start with the first boundary condition. Well, let's take a look. What do we have here? We have zero rotation. We have zero displacement. Okay. Two things at both ends. You might end up with the RA, you might end up with the M. Of course, you will get the M because what will restrain your system against the rotation? You will definitely need the M, right? The M value will be there. The RA, well, that depends. If the MA and the MB are identical in magnitude but opposite in direction, you will have the balance of the moment equilibrium, and that you will not need the RA and RB. Alright, well, if we look at this ahead of time, and if we want to cheat this one a little bit, okay, we may not do that. But if we want to do that, we can say that the RA and RB they are going to be 0, and MA is going to be equal to MB but opposite in the direction, in the sign. Alright, well, we're not gonna do that. We will just try to get the mathematics work and just follow the flow. So no need to put anything arbitrary or something we are not sure yet about it or not proven yet in here. So start with the first one. Y at x equals to 0 is equal to 0. We have the force. Okay. So 0 is equals to A times 0 plus B times 1 plus 0 minus M over P. That makes your B equal to M over P. Second, dy dx evaluated at x equals to 0. I run out of space. Yeah, is equal to 0. So this 0 is equal to AK times cosine, which is 1 plus BK. Well, basically it's not plus, it is minus BK times 0. I just don't want to be sloppy. Plus or minus times 0 turns out to be 0 anyway. But yeah, sloppy is sloppy, so that's two different things. And then what? Yeah, just that, right? A is still there, B is 0, RA is there, derivative, you get RA over P. M over P is gone because you differentiate with respect to X. So for here, you get the A equal to minus RA over PK. Alright. If you get the A, you get the B. So let me just copy this to the next page. Class number 19. I'll put it somewhere here. So the third boundary condition is y at L equal to 0. So 0 is equal to A, which is the minus RA over PK times sine KL plus the B, which is M over P times the cosine KL, and then plus RAL over P, and then minus M over P equal to 0. Well, just rearrange into the nice looking form. We'll start with the RA. RAL over P. We have the bracket here. RAL over P, you get 1 minus sine KL divided by KL. Alright, yeah, and the plus M over P cosine KL minus 1. Looks good. So you'll be able to express the RAL over P in terms of M over P. Well, you can just cast the relationship between these two things. Number 4. Differentiate y with respect to x where the x is equal to L. Alright, let's move it around a little bit. Okay. What do we have? We have the AK cosine, right? And A, well, the R is what? Minus. Okay. So AK cosine will be the minus RA over P cosine KL, and then minus M over P K not cosine, it's the sine. Okay, sine KL, and then plus RA over P. I'll just move this down. 0. 0 is equal to this. So make it L over P. In the bracket you have 1 minus cosine KL and then minus M over P KL sine KL. So again you write maybe M over P first, a little strategic planning for solution. So M over P is given by RAL over P multiplied by 1 minus cosine KL divided by KL sine KL. The first equation. Well, for the one above, for this one we can do the same thing. Make the M over P the RAL over P multiplied by sine KL minus KL. Okay, because we have the minus sign when we switch the M over P to the other side. Yeah, push that to the other side. The KL will be the common denominator. We switch around and then we get the KL multiplied by, okay, KL cosine KL minus KL, right, cosine, okay. What next? We actually can equate the M over P equals to M over P. So if you do so, I will take this one and equate to this. But pardon?
For boundary condition
Number 4, yes.
negative m over PL, because the m over PK sine PL doesn't have that
M over P
sine PL.
M over PK sine KL. What?
Yes, but you put under KL sine KL.
Mm-hmm.
There shouldn't be an L, because in the first equation
There shouldn't be what? I multiply through by the L.
So m over PL.
M over PL. Well, what I did, I multiply the whole thing by L. Okay, all right. Okay, so I equate them up. The first one, or if you want to okay, so we just need to solve this equation. Okay, you can do it the other way around, so by writing the RAL over P in terms of M over P multiplied by the coefficient. Of course, you end up with that set of function of KL equals to another set of function of KL. So we need to solve for KL. All right, that's the idea. But what is this equation? Can you solve this equation? May not. All right. So we're gonna do things in a numerical way. Well, if you are patient enough, let's see. If you want to solve it precisely, let's take a look if we can manipulate things around a little bit. But if it is too far, okay, I'll just go ahead with the numerical technique. So if you cross multiply, we have the sine KL minus KL multiplied by KL sine KL. 1 minus cosine KL multiplied by KL cosine KL minus KL. Let's see. So this whole piece is not bad. You get the KL sine square KL minus KL square sine KL equal to, I'm not sure if I'm going to bring you to where we want, but let's try. Okay, I don't promise. KL cosine KL. Well, I like to get the closed form solution rather than just go ahead to the Microsoft Excel and do the goal seeking to get the value. So first of all, let's aim for the closed form solution. Even I think we should be able to struggle out of this maze, but it's gonna take some effort. Alright, here you have what not plus, this is minus. I think I see the light at the end of the tunnel. We should live with hope, right? And what? Minus cosine. Minus, minus to minus, it is a plus. Plus KL cosine KL. Okay, first hope I solve. This and this. Okay, they must make a very good friend. Oh well, first of all, let's do this killing out. KL, we take one KL, we take this KL, you take this KL, and you take this KL, and you take this KL. So life will be a lot simpler. Well, I have alright, sine square KL plus cosine square KL, this will make 1, right? And then plus 1, which is from here, move there. Okay, what do we get now? The minus KL side goes to the other side, plus cosine KL to cosine KL, right? Are you sure that it's just okay? It's just a clean 1 cosine and KL cosine minus KL. So cosine KL, yes, cosine KL, okay, KL cosine square, okay. Do we lose anything? So this side is equal to 2, equal to KL sine KL plus 2 cosine KL. How further can we struggle? If we use the concept 2 sine cosine thing, but I don't remember those things anymore. Anyway to solve it explicitly. I don't want to jump to the computer now. Think of it a little bit. Should there be any possibility? KL multiplied by sine, so we cannot collapse these two things, right? Okay. If we substitute the 0 value, so if KL is equals to 0, you'll be able to satisfy this, but KL being 0, it doesn't make any sense. That means you have a 0 axial force, so you will vary the KL value to somewhere. So if the KL makes what pi over 2 or pi over 4, pi over 4, let's think of it, pi over 4, cosine pi over 4, okay, which is, right, jump to the computer. Okay, enough, give up. Right, so come to here. We need to find out the KL value that satisfy the requirement of the function of the KL. The function of the KL is basically given by the KL itself multiplied by sine of KL and then plus 2 times cosine of KL and then minus 2. So this function was supposed to be 0, right? We have KL sine KL. Oh, okay. So does it overrule the screen? Okay, all right. So KL times sine KL plus 2 cosine KL, right? And then you move the minus 2 to that side. So the whole thing was supposed to be 0. You get 0 when the KL is 0. And then you increase the value of KL to be something incremental like this. Well, maybe it's a little too big. 0.25, okay. You see? And then we go ahead with this. So let's take a look. 0.55. Let's plot it out. Maybe it leads you to scatter. Okay, so you can see the trend right now. It starts from 0, but it keeps going off 0 continuously. So we need to continue. So probably like, okay. And then cannot. Is there any hotkey for to do this? I think like Control D thing might work, but oh, still? Oh, no. It reversed already somewhere. Okay, so you can see this graph here. 0. Okay, you get the equation satisfied at the 0 axial force, and then you come across 0 again when the KL value is equals to 6275. We can just get down to that location, 6275 to 3. If you want, we can refine the value. So 6.2 what 76 if we want to get okay a little bit more as we are doing numerical technique, you don't get the pi being pi, right? You get 3.4 something. You don't really get that. So I try to make it. Okay, it's 252423. Insert. To 7 or to 8. Do we get? No, not yet. I think we can spare like 2.8, 6.29. 6.29 is too far. 6.283. Huh? What 185? 6.83185. Okay. Good now. Okay, thank you. Delete. This is what? 2 pi, right? So numerically, I hate this. You know, I still feel very bad about this, not being able to solve that equation mathematically. Actually, the one who's very good in mathematics will be able to just get that done, but I give up. Okay, I don't have time to do that. Okay, so that is about 2 pi. So we come back to this screen and we find that the KL could be 0, could be 2 pi. So we expand the KL, and that is a square root of P over EI. So you make the 4 pi square over here, and then you get the L square over there. You get the P over EI, so you keep the P on the left hand side and the EI was taken to the right hand side. And we reconfigure this equation a little bit. So we have the EI pi square over L over 2 square. So basically, this is the effective buckling length. Many times, well, not just many times, actually in the code they call this the KL. So the K for this case is equals to 0.5. And then if we just substitute the KL being 2 pi back into the equation, such that we can check if your RA is equal to 0 or not. Alright, so you just pick one equation, whichever, okay, the number 3 or number 4, both of them should be usable to prove our concept. So just get one. I select this one and then I paste it here. So KL is equals to what? 2 pi, right? 2 pi. What do we get? One minus cosine of 2 pi. 0. Zero on both. So you need to apply L'Hopital's rule, right? Because you had 0 over 0. Well, RA over P. If the point is that RA over P, we have a chance to get this one being 0 as well. Maybe we write the RA over P in terms of M over P first. That should be, should that? Now it is very complicated. The issue is that RA over RA seems to be 0. And then multiply by this part, even though we go through L'Hopital's rule, you might end up with something which is not 0. Whereas, well, the M over P itself was supposed to be infinity. Because when the system buckle, right, M over P will be very large. But you get the 0 multiplied by infinity or divided by 0. Let me. Well, if we apply L'Hopital's rule here, you get cosine, you get minus k. Differentiate cosine, you get the thing inside, right? So you get the KL and then sine KL in there, divide by sine KL plus KL squared cosine KL, right? But still this part here, RA over P will be 0. Well, vice versa, this thing is, if I write the RA over RAL over P in terms of M over P is infinity. So you're going to have infinity multiplied by 0. Okay, the issue will be there still. Okay, I think, let me look at this. So as of now, we have the RA M over P. Okay. Let me do this. Y equals to y of x is equal to no. If I write y let's try first. The A value is equals to minus RA over PK minus RA over PK sine KX plus M over P cosine kx plus RA over px minus m over p. This was supposed to be the deformed shape of this system. The point is the R, A and the M are not determined yet. We know the eigen value of the system. We are trying to come up with the eigen vector of this system. Okay, what if I substitute this into the m over p? Okay. So m over p out there is substituted by this. So we have the RAL over P 1 minus cosine KL and the KL sine KL. We are still having a good hope for life. Okay. And okay, it's also work the same way for m over p out there. So the m over p here will be substituted by this term. So the difference is just the cosine value, right? Alright, 1 minute. So I have minus A L over P multiplied by sine KX over KL. Okay, let's fix the first term. The second term here plus RAL over P multiplied by X divided by L. And then the third term minus RAL over P, which is the combination of this one and this one. So you have this multiplied by cosine kx minus 1 multiplied by 1 minus cosine kl, and then kl kx, okay, that's right, and then KL. I think so this is your equation y at x. Let's see if the boundary conditions is going to help us another time. We used them already, but let's see. So if y at 0, if we look at y at 0, okay, we get 0, so that is not going to help us, right? Y at 0, this is 0, this is 0, this is 1 minus 1, you get 0. So everything is 0, so that doesn't help. How about KL value is right now equals to what? 2 pi, right? 2 pi. Or if we go to KL, substitute L in there, sine KL sine 2 pi, okay, 0, right? Sine 2 pi has to be 0. Cosine KL, which is 2 pi, is equal to 1. 1 minus 1, 0. This is 0, definitely. 0 and 0. Okay. Well, this part here is going to make 0, but we have double 0 up here, divide by 0 there. I think this whole thing, if you evaluate seriously by L'Hopital's, you get 0. So the remaining thing will be substitute x by L, you get L, right? You substitute the x value by L because you have the boundary condition at the right end where the x value is equals to L and the y of L has to be 0. Y of L has to be 0. You start from this term gone, this term gone, this 0, and this is 0. Okay, denominator is 0. But you have 0 multiplied by 0, divide by 0. You have more 0 above. Well, to evaluate precisely, go ahead through the L'Hopital's rule or just plot this out in the Excel. I am pretty sure that it's going to be 0. So you have one term survive, right? And this one term that survive is equal to 0 on the left hand side. So this leads us to, let me clean out. I'll write it this way. Y at L is equals to 0. So 0 is equals to minus RAL over P. Start with the sine KL, which is 2 pi divided by 2 pi, right? Minus turns out to be cosine 2 pi minus 1 multiplied by 1 minus cosine 2 pi divide by 2 pi and then sine 2 pi. What else? Plus 1, right? Once you substitute L by substitute x by L. So this term here 0. In this 0, in this is 0. Sine 2 pi 0. Evaluation by L'Hopital's rule. This one you end up with something like the 1 minus cosine square KL cosine square of let's say 2 pi, right, over 2 pi multiplied by sine 2 pi. Let's see. You differentiate, you get minus differentiate cosine square now. What is it? let my brain differentiate cosine square. So you have 2 cosine multiplied by minus sine 2 cosine 2 pi, and then another thing is minus you need to take it out, right? 2 pi and then sine 2 pi, is that right? And then plus, it was supposed to be plus 2 pi. Okay, differentiate. Okay, you get this function down, boop, and then differentiate the thing inside. Okay. So we have the cosine and sine. How about the denominator? Denominator, differentiate, you get sine 2 pi plus 2 pi cosine 2 pi right? Supposed to be this one, right? Differentiate this first term, you get this, and then you have the first term multiplied by differentiate the second term, you get this. Differentiate a plus b, differentiate a times b, you get dA a times db plus b times dA. Huh? 2 pi is constant, but you need to when you apply L'Hopital's rule. 2 pi what? 2 pi square. Differentiate what? Cosine. Oh, then we get 2 pi square. The whole thing square, right? Okay. So sine 2 pi is 0. 2 pi square cosine 2 pi is finite number, non-zero. Okay. And the part up there, you multiply by sine 2 pi, has to be 0. So 0 divided by finite number, you get 0. So we are sure that this whole thing is 0. According to what? According to the L'Hopital's rule. Is there anything? One minus cosine square 2 pi. So you differentiate 1, 0.
Before that, how did it 1 minus cos square 2 pi?
This multiplied by this. 1 cosine minus 1 and 1 minus cosine. So Okay. It is okay. You will have another term, okay, which is 1 times 2 times 1 times cosine, right? 2 times 1 times cosine. Differentiate that term, it turns out to be sine and 0. Okay, yeah. So to be precise, yes, I need to incorporate that, but still get 0 as the numerator term. Okay, thank you. So should I just rewrite it? 1 minus 2 times cosine 2 pi. Then we're supposed to be plus, right? Cosine squared 2 pi divided by 2 pi sine 2 pi, and we differentiate we get minus 2 times 2 pi and then sine 2 pi plus 2 cosine 2 pi and then what? Cosine and then sine 2 pi divided by differentiate the 2 pi, which is like a x, you get sine 2 pi and plus 2 pi differentiate sine, you get cosine 2 pi. And evaluate this. 0, 0, 0, not 0. So the whole thing is equals to 0. Okay, feel good.
Sir, for this one, the P is dependent on the K, no? P
The P is
depend on K, depend on 2 to 4.
yeah, because the P is a function of K, and then
So while we are putting the L posterior rule, we have to consider that one as well.
wait, why what? Why did I what?
No, while we are putting L posterior rules, we have to consider P also.
Why do we use L'Hopital's rule? Because we have to consider the P also. Yeah, and the P is equals to K square, right? Oh. Let me find the explanation then. Do we really? First of all, P is well, K square, right? P, if we get the EI there, it's a K square. And the KL we have is equals to the finite number, right? So this denominator scale outside the 1 over KL square will be one finite number that will not produce any problem like a 0 denominator, right? So if we add it in, this part will not be the part that is troublesome. The troublesome part is something that is divided by sine KL or divided by 0. Yeah. So I still think that we just apply L'Hopital's rule over this part here. But it is a good observation, yes. If we want to incorporate everything in, I think it might just take a few more steps for L'Hopital's rule to just get there. Or maybe it doesn't, but just more complicated. And that confirms that the P as it is not 0, L is non-zero, so the RA has to be 0. So we don't have a shearing force during the buckling of this system. Okay. Actually here, the better explanation maybe that makes everything easier a lot. This part are known to be finite number. Alright? Left hand side is 0. Okay? So you can divide through by L over P. You can just simply get rid of it, because this part, as it is non-zero value, you can throw it out of your consideration. 0 equals to 10 times A times B. You know that 10 will not alter your solution. You just get rid of the 10. So the L over P will not just come in and involve with your solution. You just divide them out, right? Like the 10. Whatever number, if it is finite, and we are sure that it is not 0, you can just get rid of it. So this is more solid in terms of mathematics. How do we know that RA depends on K or not?
RA is dependent on K. K
Well, RA we set it at the very beginning of the derivation to be one unknown constant. We know that RA is going to be the function of K. We know that P is also going to be a function of K, right? But we try to solve for this number. If RA turns out to be the function of K, then we should be able to find the RA in terms of K function. The point is that over here in this problem, RA is one value. Likewise, for M is going to be one value. You look at the form of the equation. M and RA are related to one function here and there. So when you want to solve and express RA in terms of KL, it's not possible, because if you equate MP to MP, then you have RA on both sides. Finally, RA cancel out, right? You will not get the function of RA in terms of K. You equate these two pieces, RA, these terms will cancel out. It will not be there anymore. Or if you write the RA in terms of M over P and the function of KL, RA will not exist anyway. So it leads to some suspect that RA is going to be some value. But what is it? Then that's why we try to go many ways to find and verify that RA is essentially 0. Do you want to verify that M to be infinity? It could be, but okay, it might waste a lot more time. Well, if the RA is 0, well, let's come back to here. I'm not sure if everything is written in terms of RA right now. M over P. If RA is 0, how about the buckling shape, the eigenvector of this one? If it is all 0, then it's not good. I think I used to be able to come up with this. I doubt what was wrong. Any point? You get Y in terms of M and RA. Okay, that's not a. And you plug in the KL value. Okay, right. And then what? If we substitute, let us look at this way. Y of x, right? Let me rewrite this. So this is your solution, original one, minus M over P. Before we substitute the RA in place, because previously we do not want to keep the M over P term, we substitute the M over P by the function of RA and the other things. Right now we get the RA being 0 and this RA being 0, so we will have this equation 1 M over P multiplied by cosine kx minus 1. Yeah, is it kx? Yes, okay. So your function y of x is equal to this. m over p, one number. Okay, m could be infinity, very large number. Let's look at the distribution of the y function. Your y function right now should be like this. So x equals to 0, x equals to L, and this is equals to m over p times cosine of k, which is the k value is 2 pi over L, 2 pi over L multiplied by x, and then minus 1, just like that. So basically it is 2 pi x over L. And x over L ranges from 0 to 1. So cosine from 0 to cosine equals to 1 full cycle. Start from cosine equals to 0, cosine the whole thing equals to 0. You get 1 minus 1, you get 0. And then cosine value varies all the way until the maximum cosine, the minimum cosine value is minus 1. That is going to happen when x over L is equal to 0.5. Alright? And then the value will be coming back again until the cosine gives the 1. So 1 minus 1 equals to 0. So let's plot it on Excel to see how this looks like a little bit. So to plot on Excel, so as we try to plot this in Microsoft Excel, we found the shape of this function being something like the following. Not the best one. Even worse. Ugly. Okay, give me one more try. Where is the center? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there. So this, so this is center, and so we terribly ugly. Okay, well, this is not the drawing class, but so this shape form a half sine buckling. So when we count, when we evaluate the effective buckling length, we just look for the length that construct the half sine curve. So this is your half sine, and it takes from one point to the other point there, and the distance is 0.5 L. So the K for you for this case is 0.5. So you stuff in the K value. Instead of L alone, you have the KL. Well, just make sure that you differentiate these two K. The K that is equals to square root P over I, one thing. Okay? By chance, the code used the K also as a parameter that control the effective buckling length. Okay? This K will be multiplied by L. Well, by chance it is KL again, but it is not square root P over I multiplied by L. So it will be just some number that determines your half sine, length of your half sine. Okay, so that's it for this case. I think to make it looks better, I should just copy the Microsoft Excel plot and put it here, and that's gonna make a better look. I just capture it in Line Messenger and then send to here, copy, paste, get a nice picture. Okay, let's see if I want to do that. Yeah. If my desire drive me to go that far. Next. What else? We have the pin, we have the fix. We try pin and fix. Basically, we will just spend this class finding the buckling load by solving the equation, the governing differential equation like this. Later on, once we finish this class, we will use the stability function to find the buckling load. So using stability function, then we just do everything in the matrix term. We formulate the stiffness matrix of the column structure, and then we solve the eigenvalue of the matrix. You'll be getting eigenvector, and then both eigenvalue and eigenvector. So that will be another approach, but we just spend today, okay, this class today on this differential equation. Try to solve it this way. Pin and fix support. One side pin, one side fix. Load P, P as well. So over here, this time I think we can expect RA could be there, right? Nothing guarantees that moment. Well, first of all, at the pin you don't have moment. At that right end you have moment. So nothing is going to balance except just the shearing force. So it will come in. is equal to 0. So boundary condition, y at 0 equals to 0. 0 is equals to a 0 plus b 1 plus 0 minus m over p Well, we want to use the m over p equals to 0 real bad for this one. We know that m over p here has to be 0. We can use it after many times that we try by following a proper mathematical procedures. I think we can use this privilege now after quite many times of being a good boys already. 0, so that makes your b equals to 0, right? A multiplied by sine plus b cosine plus ra, well, that's 0 minus m over p, and m over p has to be 0 this time. Okay, b is equal to 0. Number 2, we have the 0 moment, that is the second derivative of y with x evaluated at x equals to 0 has to be 0. Moment is equal to 0. 0 is equals to a k square minus sine 0. The b term is not there. Rax differentiate twice 0. M over p differentiate 0. So basically you don't get anything from this one here. No information obtained. Or basically I think you obtain, if you want, bk square cosine 0, which is equals to 1, right? And then plus 0 plus 0, because the RA term differentiate twice 0, the M over P differentiate, you get 0. So you get just this. That makes the part here be 0. So again, you get b equals to 0, right? Even without any cheating technique there, then you still get b equals to 0. Or you can say that if b equals to 0, m over p has to be 0. But this is pretty nonsense. You know that. Number 3, y at L is equal to 0. So 0 is equal to, okay, we are sure that b is equal to 0. So we have the a sine kl plus ral over p minus m over p, which is 0, right? So that is going to make the a equals to minus ral over so we never get the A. Okay, alright, and then 1 over sine KL. The fourth equation we have dy dx x equal to L. So we have the AK cosine KL plus RA over P equal to 0. So I bring this down. And that makes the substitute the A value in there. So I have the minus RA KL multiplied by RA over P, take it outside, RA over P KL, okay, cosine KL divided by sine KL, and then plus A over P. So we have two possibilities, right? We have the equation inside 1 minus KL cosine KL over sine KL. If RA over P is equal to 0, then you get trivial solution. You don't have to do anything. If the RA is just 0, then this term turns out to be nothing, doesn't make any sense. So this term will be 0. So let's work on this a little bit. You have 0 equals to 1 minus something, or sine KL equals to KL cosine KL. You just move one to the other side. To solve for this, again, come back to Excel, construct two columns. The first column is the KL value, vary it. Second column, the function value. So find out the function values that satisfy, you move everything, you move the 0 equals to KL cosine KL minus sine KL, and this is your function. to plot. So once the function satisfies this criteria being equal to 0, that is the KL. You get that KL value that satisfies this function condition. I don't want to switch back and forth. It's just confusing when I edit the video. Do you want to see, or do I just need to tell you that I get this number? You don't like that, right? It is painful. All right. Let's we start over here then. We'll just copy this one, make another sheet. Maybe I do not have to delete it. So I change the function value, this function to be the KL multiplied by cosine of KL, and then minus sine of KL. And then, okay, so your graph shift, and then let's look up for this 0 value, 4.475. Somewhere around here between 4.475 to 4.5. If we want, we can try this. It could be at the cell here. You can go to formula. Is that right? It's not in here, or is it in data? What if analysis and goal seek? So we need to set this cell to be 0 by changing this cell. But goal seeking will just bring you to the probably the closest value. So this is your initial value. We'll see if it's gonna bring you to 0 or to that 4 point something. Okay, it brings you to target value 0. All right. What? And why isn't this change? Oh, it is closest to 10.9. I put it maybe somewhere like 4.3. Initial values there. And do the goal seek again, and by changing this cell. Okay, 4.93. So this is equal to what? Divide by pi. 1.43. So the KL value is equal to 1.4303 pi, and if you square this up, it is 2.046 pi square. This is the P. You have the L square down here and EI over there. And then you take the pi square EI, you group it up over L divide by 2.046. No, you need to take the square root of this thing first. So you have the L square over 2.046. Okay, and then you check. Oh, sorry, I didn't switch it back. Let's say 1 divided by this value is this one, and then you take a square root of this value 0.6999. Okay, then I just bring you back here. Doesn't come back. Okay, so the KL equals to 1.43. To change from KL to P, you square both sides up, you get this. Okay, and then you move the 2.046 down there. And you take the square root of 1 over 2.046, you finally get pi square EI over 0.7 L square. This is your K for the pin and fix column. So let's check what might be used to get the A value. We found that B equals to 0. A we didn't get it, right? If we want the RA, if we want the RA, let me check. RA will be infinity for sure when you solve. Right, because RA, the moment will be infinity at the base. RA will also be the infinite number. But let me check the deformed shape. So the deformed shape of this one, A is finite number, B is 0, MOP is 0, RA is there. So Y of X is equals to A, which is minus RAL over P, okay, minus RAL over P multiplied by 1 over sine KL. This is A, and A is multiplied by sine kx, right? A sine kx plus B cosine kx. The thing is that B is 0. It's gone. The next term is plus RA x over P. Or if I arrange this into RAL over P multiplied by X over L, that is going to work. The M over P term is basically 0. So let's rearrange this and we get the RAL over P. Alright, multiply by by 1, which is RL here first, X over L, no, not 1, X over L minus psi K X over psi KL. Knowing that the KL value is equals to 14303 pi, 1.4303 pi, that is going to plug in. And how about the psi term at the top? Let's write it down in terms of X over L. Psi K is equals to 1.4303 pi multiplied by X over L, right? So this term will be infinite, will be large number. We don't care, it is a scale. We need to plot and see just this term inside the bracket. Excel again. Alright, we switch back to Excel. So we use this sheet. We have the X over L ratio. Now I'm going to write the function of X, which is equals to X over L minus sine of what? Sine of X over L multiplied by 1.4303 multiplied by pi value. And then I divide that out by the sine of 1.4303 multiplied by pi, and that's it. Double click. Boop. Yes, there you go. You get this that you want. So, makes sense? You have the angle, and over here 0 displacement and 0 angle. So it match with the boundary conditions we post there. Deformed shape makes sense. So we can just copy and put it in the note. Okay.